Daily quiz is up. Good to We're the state that I'm referring to, all that mathematics. Like that the French pronunciation of the fine. Yeah. Hayden, sorry, thank you all. I'm like I said, I'm terrible names, but I can try, I promise. Sean Day. Is that correct? Good. Do you not feel like Sean? How do you do that? Michael. Michael here. Trying to figure that showing up. And then Brandon. All right. Okay. Right. It's 11 or 10:02. I'm 11:02. I'll give you all 5 seconds just in case you want to change answers. 3, 2, 1. Locking answers now. All right. True, false, or not enough information to determine? False. What is the element I'm trying to say is in this set? It's definitely one. It's set containing one. The element one is in this set, absolutely, but it's the set containing one. Okay, that was one of the concepts we talked about at the end of class, right? Where we're allowed to have set within sets. I mean, we have it here, right? This is representing what set? So the natural numbers, which is 0, 1, 2, 3, and so on. What does this represent? Integers. Yeah, so use that set of integers. So again, we can have sets inside sets. They can be a mix of various objects. It doesn't matter. Did Michael? Yeah. Yeah, okay. Good. Showed up. But in this case, the set containing one is not in that set. So this would be false. So, what questions do y'all have for me? Everyone saw my announcement about the homework? All right. And yes, no, there is potential storm coming up, but You should, after today, be able to complete most of it and finish it all on Friday. It doesn't look like the storm's coming until Saturday evening, Saturday night, obviously, unless things change. So don't use it as an excuse to try to get an extension or anything on that assignment. You should be working on it already. All right. Something was due Monday, then you'd have balance potential. All right. So we're still talking about sets. Next thing we're going to start off with today. What does it mean to be equal? So two sets A and B are said to be equal if and only if they have the same elements. And this is just denoted how you want it to be. A is equal to B. Again, just remembering we like to use capital letters to denote sets. So, and just another way to think of it, right? They have to have the same elements and means exact same. There can't be anything missing between the two. In sets, does it matter what the order is? No, they're unordered in themselves. So something like the set containing 1, 2, and 3 would be equal to the set containing 3, 2, and 1. Is the element 3 in both of those sets? Yeah, it's element 2 in both those sets. Yeah, it's element 1 in both of those sets. Absolutely. What about this right here? Leave that blank. So I have a set containing 1, 2, 5, and 7, set containing 7, 5, and 1. These two sets. No, locked. Yeah. Element 2 exists in one set, but it doesn't exist in another. So if I wanted to give a justification for it, I'm going to be a little slide, say let that first set just be A, second set B. These are not equal. Because we have 2's in the set A, but 2 is not in set B. And it's pretty easy to spot in a roster method if two sets are equal or not. Right? Just look at the elements. But if it's not in roster method, how do I go about showing two things are equal? I just have to go through and show the following statement. I'm going to put in parentheses just to make sure that it's grouped together. Just what we got from the statement of that definition, two sets are equal if only if everything that is in A is in B, and vice versa. Everything that's in B is in A. That kind of leads us into the next definition because, okay, well, we have this concept of both directions going on here. Everything A and B into A, and we're equal. What about if it only was true in one direction? Everything that's in A is in B, but not everything that's in B is in A. Just like we saw with that example, right? 1, 2, 5, 7, 7, 5, 1. What was that feeling? Probably know what we're going to next. Yeah. So if we relax that definition just a little bit, instead of having that double inclusion, that biconditional, just into a conditional, you get what is called a subset. So a set capital A with a subset and set capital B if and only if every element A is an element of B. How we denote subsets, kind of think of it as a rounded out less than or equal to symbol if you want to. When I first learned it, I think of it as like an elongated lowercase c, so a line underneath it. This is the symbol that we're always going to use as subsets. So we get three things here. Follow these relationships. First up, if you want to deal with subsets, if I want to show that A is a subset of B, then all I need to do is show if I choose any general element from the set A, show it must have X as an element of that set B. Every single thing in A has to be in B. How would you show something is not a subset? So how would you show if A is not a subset of B?
You put a line through the, okay.
Oh, well, yes, notationally, that's how we would show it. But I make the claim that a set A is not a subset of B. How would I go about justifying it, proving it to the reader? So there can be many elements in B that are not. And all I need for A to be a subset of B is everything in A, B in B. So you're kind of looking in the right direction, sorry. Well, if either element in A or B, then that's not affecting the definition of subset, right? Let's go back to the definition. A is a subset of B if only if every element of A is an element of B. So how would I not satisfy that definition? How would I not satisfy that statement? I can find an element in A that's not in B. And all I need is one, right? Because the definition of subset says every. The opposite of every, the negation of every is some. I need at least one. And the last thing, we can use this idea of subsets to show two sets are equal. So to show the set A is equal to set B, especially if it's a not in roster method. First, show A is a subset of B, so everything that's in A is an element of B. And then what else would I need to show? Finish up that definition. Yeah, Kimberly's got it. Show the opposite. B is also a subset of A. If everything that is in A is in B and everything that's in B is in A, then I have to conclude the only logical option is that it's satisfied. So, some examples. Well, that set 751, it wasn't equal to that other set that I gave you. But it was a subset of the set containing 1, 2, 5, 7. They also have the set containing 1, 2, and 3 is a subset. The set containing 3, 2, and 1. Why is that still true? We said they were equal, right? Why is it true that they're subset? Or this is a subset? Everything that is in this first set that I list, 1, 2, and 3, and then one with that second set. And I also flip this around. 3, 2, 1 subset of 1, 2, 3. Absolutely. Because all I need to do is satisfy that definition of being a subset. I'm not trying to overcomplicate it here. Everything in that first set needs to be an element of the second set. Set of positive integers is a subset of the integers. Set of rational numbers. A subset of the reals. A set of natural numbers, not a subset of positive integers. Why? Why is that a true statement? And natural numbers are zero to positive integers. So 0 is an element of the natural numbers. And 0 is not an element of positive integers. What questions y'all got for me so far?
Right, what he was doing,
This one right here?
sorry, I mean the number 2, like, the one the number.
Oh, gotcha. Here. Show something is not a subset of another set.
Yeah. So, so you said like how it's subset, sequence subset. So, so it to be a subset of B. If I only get every element of A is in B. So, yeah, 1, 2, 3, 5, 7, and A, and 1, 2, 3, in B. That would still be a subset.
Well, it depends on what you're saying is a subset of what. So let's write it out for everyone. Said A was
1,
2, 3, 5, 7. And B What'd you say again? 1, 2, 3. I can write a subset relationship, but it's going to be just one specific direction. I'd be able to say B is a subset of A, everything that's in B is A. But A is not a subset of B because what's in A that's not in B? 5 or 7, right? You can pick anything, but you just need at least one element. And that last one is true because 5 is the element of A, but 5 is not an element of B. What other questions do I got? So next up is our concept of 0 when it comes to sets. 0 when it comes to addition is the concept of nothingness. So what is the equivalent when we consider sets? Well, something called the empty set. So the empty set that contains no elements. And there's two ways you can denote the empty set. First and most popular is the 0 with a line through it. Again, kind of riding on that concept of 0 for nothing. But I don't want to differentiate it from the number 0 with a line through it. Or some people even list it as roster method. But if the set has nothing in it, well, it's just going to be the notation. Two curly braces with nothing in it. That is how we can denote empty set. And there's actually some interesting things about the empty set when it comes to that definition of subset. So we're going to prove these. We're going to have two statements. First, that the empty set is a subset of any set. And second, any set is a subset of itself. Break down that first one for a second, though. What does it mean to be a subset? A is a subset of B if everything in A is an element of B. Everything in that first set is an element of the second set. But what elements are in the empty set? Nothing. Why is that true? Well, like I said, we are going to prove it, but you know, even a small technique you can do in homework when they start getting you to write some written proofs. Start with the easier statements, right? Which one do you think is easier to prove? Number 1 or number 2? Number 2. So let's start with our preamble. What do I get to assume from the statement of my theorem? Just got a set, right? Well, if I want to show, I'm going to write it in green just to make sure. Remember our goal for the second one. Show A is a subset of A. which means I need to show that every element, in the first set, an element in the second. Well, then I need to pick an element from the first set and verify that it is an element in the second set. So I'm picking an element from the first set. Let X be an element of A. Well, what does that mean? Is that an element of my second set? It shows an element from my first set. I need to deduce that it's an element of my second set for that statement to be true. Well, I let X be an element of A. Is it an element of A? Yeah. Logic. Take an element from the first set. It's an element of the second set. Did I tell you what that specific element was from the set A? So it's anything from the set A. So I keep it general. I showed it had to be in that second set, which happened to also be A itself, right? So by definition, it satisfies subset. So any set is a subset of itself. Let's get to that first one. Yeah, it's supposed to be weird. I love math. So if I wanted to do it by definition, do this proof by definition, I would need to take an element, any element from the first set, show an element in the second set. But what's the issue with that premise? I would be able to take something from the empty set, right? But what elements are in the empty set? There's nothing there. So I can't actually do a direct proof. Well, there's no if-then statement here, so I can't do a contrapositive like we've done before. But there's another technique that also starts to actually apply. We've done it here. I can't remember if we did it. I did it here. I did it past. Contradiction. We can do a proof by contradiction. But assume the opposite, negate the statement, and then show that with that negation, there has to be some logical fallacy. And if that's the case, then the premise was wrong, i.e. the negation, which means the opposite of the negation, original statement, has got to be true. So to make it clear, we realize we got to do a proof by contradiction. Let's make sure everyone understands this when we're writing it out, whoever's going to read it. We have proof by contradiction. All right, and get contradiction very small on the right-hand side, but hopefully you know it. Then I need to assume the opposite of the statement I'm trying to prove. Well, if the statement I'm trying to prove is the empty set is a subset of any set A, then what is the opposite? To assume that the empty set is not a subset of the set A. What does that have to imply? Say that one more time, community. Yeah. This implies there exists some element in the empty set Let's say such that. X is not there. There's an element in the empty set that is not in set A. Oh, wait a second. That is hit a logical fallacy. What's in the empty set? Nothing. But if the empty set's not a subset of A, then that implies there exists an element in the empty set. There can't be anything in it. So that creates a contradiction. It creates a contradiction with the definition of it. There can't be anything in it. If it's a contradiction, my assumption, and I assume to get to that contradiction must be false, i.e. subset empty set is not in subset set A. Therefore, or thus, we have that the empty set must be a subset of that set A. So the empty set is always a subset of any set. And when I'm done proving things, what do I do at the end, or put at the end of my proof? Where? Nice little black square, help the reader know I am done. No more arguments to be made. What questions I got, Jill? Get just a little bit more practice. Definitions. And make an appropriate statement. Following sets. So first up, we're going to let A. Set 1, 2, 3, 3, 5, 5. We're going to let B. Set 1, 3, and 5. Second one, we're going to let A be the set containing 1. We're going to let B the following. And lastly, we're going to let set A be the empty set, set B be the set containing the empty set. When I say make an appropriate statement, I mean using the quality or subsets. Take one more to the copy, you can finish writing this down. Go ahead and start thinking about the first. What's an appropriate statement I can make with those two sets A and B? So B is definitely a subset of A, that is true. Anything else I can say? Why is that the case? What is in A that is not in B? If that's your part. You're saying 1, 3 is an element of A, is 3 not an element of B? 3 is definitely B. So 1 is an element of A, 1 is an element of B. 3 is an element of A, 3 is an element of B, no matter which one I choose. In there, is 5 an element of A, 5 an element of B. Yeah, so I also have A is a subset of B. If I know A is a subset of B and B is a subset of A, what can I also deduce? 2 sets right. I'll admit this one's tricky because if you really dig deep into set theory, one other condition you can put on the definition of the set that you don't have any repeating elements. That changes things up, but these would still be equal because if I reduce the set A down so there's no repeating elements, it'd still be the elements what? 1, 3, and 5. All right, what about those second pair of sets? So that first set A is the set containing what? Set containing the set containing 1. What is the set B? Be a little bit careful, but it's this, you got it pretty much. The set containing 1 and the set containing. What's an appropriate statement I can make with these two sets? Yeah, A would be a subset of B. Would be a subset of A. And every time I make a claim like that, in Ross, at least in Ross method, I still want to justify it. What is in B that is not an A? Yeah. So 1 is an element of B. And 1 is not an element. Okay. What about that last one? Well, be careful. But no, actually, no, sorry. You're correct, because what does our theorem state? Yeah, you said it's a subset of everything. So A is a subset of B. B is a subset of A. What's the only element in B? An empty set. There's still an element in there. Is there an element in the empty set? No. No. So there's an element in set B that's not in the set A. Mhm. That's, are you talking about for here? Yeah. I mean, you can write it the other way, which would be, I would argue it's not clear. That is another way you can write it, sure. There's one more true statement we can make. No, look at it. Questions you got from me? Well, next up. The thing that we're gonna care about is find out why. Something called the cardinality of the set. Anyone have to know what cardinality is or what it's defined as? Sorry, good set. Yeah. We'll let A be a set. There are exactly n distinct elements in set A. When we say the cardinality of that set A is that value n. And if I want to say I'm looking at the side of the set and the cardinality of the set, what I'm going to do notationally to fix that, just put it inside absolute values. The absolute value of a set, well, that's not really absolute value, right? I'm just trying to hijack it for the algebra days. We're just talking about how many distinct elements are in there. Now, right next to where I put that little weird looking star, I say if what? I want someone to interpret that for me. The cardinality of A equals n. The element of natural numbers. So cardinality of A is equal to n, which is a natural number. We then say that set A is a finite set. There is a finite number of elements in there. And correct. If A is not a finite set, then what do you think you call it? Infinite set. We'll give us three sets here real quick. We're going to determine the cardinality of each of those three sets. The first thing I need to do for that set A is figure out what it's talking about. Make sure we're reading it correctly. So someone interpret for me what this set A is containing. Yeah, all those numbers are correct. Pile it all together. All positive integers, less than 15. How many positive integers are there less than 15? It's 14, 1 through 14. So the cardinality of the set A is 14. There'll be 14 numbers in it. I try to write this out in the roster method. 1, 2, 3, all the way up to 14. What about the set B? And this is assuming it's English alphabet. Any letters you have in English alphabet? So the cardinality of that set B would be 26. That third set, I'm going to just kind of ignore the C. What's the cardinality of the empty set? Oh, nothing. Well, the empty set contains nothing. Not one, because that would indicate that there is an element. Zero. Cardinality of the empty set is 0.
So the empty set containing, or the set containing empty set.
So if you look at cardinality, that containing an empty set, I think there is one element in there. That one element. I got one more definition. Any questions? So, oops. Myself. Given a set B, the power set of the set B. The set of all subsets of the set. So how we denote this? Nice little curly P. A little tail coming off the top. P for power. Power set of the set B. We can do a quick example. Let A be, someone give me 3 elements. 3, 4, 5. Question here is, what is the power set of A? Like, what are all the elements of the power set of A? Well, power set is just the set of all what of A? Subset. It's going to be the set containing all subsets of A. Now I just need to start listing off subsets of A. Well, what are 2 subsets we're already guaranteed thanks to that theorem that we put? Empty set and so. So the empty set is a subset, and the set A is a subset. Those are not the only subsets. What's another subset of the set A? Set containing 3. Set containing 3 would be a subset of the set A, because 3 is an element of this set, and 3 is an element of the set A. That's another one.
A set of 4, set containing 4, and a set containing 5.
Yeah. And that'll take care of all of my subsets of cardinality one. Now I gotta step up to, okay, what are all the subsets of cardinality two?
3 and 4,
Yeah, that's the
2,
only.
5,
Oh. Four, five. And that's it. So this would be the power set of that set A. All right, it is, again, it's 10:50, so perfect time. Okay. Friday, we'll start talking about intersections, unions, set difference, do some examples, probably get the complements as well. Now round you off so you can finish that homework on Friday. But I can guarantee you the first half of that homework doesn't even deal with sets at all. They should already be started. Okay. If you have any questions for me, feel free to stick around and ask. Otherwise, get on out of here. I'll see you Friday.